So now we want to deviate from vectors for a while and talk about the main thing we're going to talk about this semester, which is multivariable functions. So, of course, at this point, you should be familiar with one variable or single variable functions, right? That's what we did all in Math Tools 1 or Math Tools 2. So this would be just something like f of x equals x squared or whatever, right? So the idea is that when we say that there's one variable, we mean that there's one independent variable, right? So we would define this as like y equals x squared. And from that, we could make a graph. We could get a set of points, right? Well studied at this point. So when we open it up to multiple variables, so naturally we can start with two variables, but we can push it further than that. A lot of the examples we'll look at are going to be two variable functions, just because it's not easy for us to visualize, but it's possible for us to visualize two variable functions. Because as we looked at in the three-dimensional coordinate system video, right? We can make a three-dimensional graph of an object, right? Especially using computer technology. But we can't do that with 4 dimensions or 5 dimensions or 6 dimensions, etc. And once we get into 3 variables, we would need 4 dimensions because we would have 3 independent variables plus the 1 dependent variable. So for that reason, a lot of our examples will stay in the 2 variable realm, but a lot of this would generalize pretty easy to 3 or 4 or however many variables. It really wouldn't change too much. So anyway, so if we wanted to look at a 2 variable function, we usually would call it f of x comma y. So y now is being used as an independent variable as opposed to the dependent variable that we're used to seeing it as. So that'll take a little bit of an adjustment. So f of x comma y, maybe we look at like x squared plus y squared, for example. Okay. So we can define, again, the set of points z equals x squared plus y squared, and then we can make points based on our three-dimensional coordinate system, and we could graph this function, but it would be a lot more complicated than graphing a two-dimensional function. So it's not something that we typically would do by hand, though we theoretically could. It's something more that we would do maybe with a computer, graphing calculator or something like that. So with that being said, I'll switch over to exactly that here. Okay, so this is not the one we want to look at here. So I'll delete this in a second, but just as a reminder of what this coordinate system looks like, right? So we have the x, the y, the z. Let me get rid of this. So this is generally the coordinate system. Okay, so it's just on, just going 3 in each direction here. So we're going to add, this is x squared plus y squared, so it's going to look something like this. I think we looked at this one in that introduction video, if I remember correctly, but you can see it kind of has that same general shape that a single variable squared function does, right, with the parabola, but now it's in 3 dimensions. Okay, but it's not really too surprising that it keeps, that it has this shape, because that's kind of what we would expect. Okay. So again, very complicated to do something like this by hand, but we can do it with a computer system, computer graphing calculator like this. You can do this in GeoGebra too. I'm just not as familiar with that system. So we can still talk about like domain and range, and in fact, domain and range are still pretty important, but they might not be so easy to, find. Like in this case, we when we're looking for domain, we think of the same kind of domain issues that we would have with one variable, namely, like, is there a square root? Is there a denominator? Is there a logarithm? All things that limit the numbers that we can put into them. In this case, there's no limit. We can put in any number we want for x, and we can put in any number we want for y. Okay. So the domain of this function, well, x can be any real number. So if you remember this symbol for the real numbers, where you kind of have the double bar on the r here, it makes more sense when it's typed. And y can be any real number. So altogether, we would say there's a few different ways you can write this. Kind of the idea is that you have these x, y points that can be in r, we would say cross r. So like this is for the first coordinate, and then the second point is for the second coordinate. But the more common way to write this would be the x comma y is in what we call R2. Okay, so that's kind of the idea, is now with 2 dimensions we're working in R, or with 2 independent variables we're working in R2. Okay, so R2 typically refers to, okay, you have the real line and then you have another real line. So like this is a representation of R2. So before that was like our entire function, right, with the domain and the range together. Now our domain itself is in R2, and our range is still going to be in R, because that's just distilled into a single real number. Sometimes you call it R1 or just R. So altogether in our 3-dimensional system, we are working in R3. Okay, so that's just referring to how many coordinates you have, basically. So our range for this system, you could see it, on the graph, that just like with the regular parabola, it starts at 0 and then it goes to infinity. Okay. So let's look at some other functions here. So if we have f of xy equals 3x plus 5y plus 2, for example. So this is the one I had graphed already when I pulled that thing up. So this is a linear function. It looks very much like the linear functions that we have with one variable. And when we have a linear function in 2 dimensions, it's a straight line, hence why we call it linear. But when we open that up to 3 dimensions, now it's going to be a plane. Okay. So the domain and the range we expect to be the real numbers here. So this would be R2, and the range would be just R. So if we look back at that, so this is 3x plus 5y plus 2. Then you can, if you get the angle right, you can see that this is now a plane. Okay, so looking at it from the side, it's hard to kind of switch it that way, but if you look at it from the side, it's going to look like a straight line. And then you open it up into 3 dimensions, now it's like infinite straight lines going down that direction, which makes it a plane. Okay. So a linear function with 2 dependent variables becomes a plane. And you could see there that the domain and the range is all real numbers. It kind of cuts it off, so it's, we don't put like arrows on the end of it like we do with lines. So it's it can be a little bit harder to tell exactly where it cuts off. But usually, that's kind of where we're trusting the math. So one more function here as an example. F of xy. So this one does have a domain issue. Or I'm sorry. No, that was right. Okay. So yeah. So this one does have a domain issue. So we have the square root of 9 minus x squared minus y squared. Okay. So we have to be careful with the domain here, mainly because the square root cannot be negative, right? We still have that same restriction. So we need to know exactly what number can we plug in for the domain. And it's going to be a little bit tricky because depending on what we plug in for x, that's going to limit what we can plug in for y, and vice versa, right? So like we could theoretically plug in a lot of numbers for x if we kind of compensate for that by plugging in some other value for y. So if we were to do this mathematically, so if we look at the domain here, we know that this must be greater than or equal to 0 because that's the limitation of the square root function. So if we just kind of rearrange this, we'd have x squared plus y squared is less than or equal to 9. Now you might be familiar with this function. Specifically, if it was equal, this would be a circle centered at the origin with radius 3. Okay. So that's going to, and because this is less than or equal to, it's less than or equal to the radius. So this is the inside of that circle with a radius of 3 centered at the origin. Okay. So that tells us what points we can use in this function. So points that are within that circle. So we can kind of draw our domain here. Right, so we just go out 3. So it's centered at the origin, radius of 3 on every side. So this tells us all of the xy pairs that we can plug into this function. So for example, 1, 2 is a number that we can plug into this function, and we can test it. 9 minus 1 squared minus 2 squared is going to be 9 minus 1 minus 4, so minus 5, so square root of 4, so we get 2. We can see that we can't plug in 4, 0, for example, right? Because if we did, we'd have 9 minus 4 squared minus 0 squared. So this would be 9 minus 16. So this is the square root of negative 7, and that's not allowed. Okay. So if we go ahead and look at the graph of this one, okay, so we'll do the square root of 9 minus x squared minus y squared. Okay. Then we can see this function here. So a little bit strange, but you can see that, we're kind of cut off at those XY points around 3. It's not going any further than that. Again, it's a little bit hard to tell because it's only graphing part of this. Actually, I have my range here set at 3. So if I just bring it out to 5, oh, that makes it better. So you can see that it's still not going out past 3 at all, right? And then I just increased my intervals here and it didn't change at all, as you can see. So the range is a little bit tricky here. It looks like it's going to be basically from the most it can be is 3, which would be if x and y are both 0, right? And then the smallest it could be would be 0 if you were on the boundary of that circle, right? So, now that our domain is 2-dimensional instead of, one-dimensional, like normally it would be like an interval when we were looking at 1 dimension, right? We'd consider the endpoints of that interval. And like when we were doing optimization, for example, with single variable functions, we'd have to consider the endpoints of the interval. So now that we're opening up to 2 dimensions, we have to consider the boundary of our area. Okay, so here it's a circle, so we have to consider the boundary points of that circle. So all the points on the boundary. And that obviously increases the number of points we have to consider quite a bit in those kind of scenarios, where here you just have 2. Here you have really an infinite number of points. So we can see, just by adding this one extra variable, the complexity increases quite a bit. So it's going to kind of limit the stuff that we can do, but we're also going to see that a lot of the things that we want to do have a pretty natural extension from the one-dimensional case.